Membranophone, Idiophone is the source filter model. Most of musical instruments can be modeled as a system in which a source that will create an oscillation and a filter, a system with natural frequencies, interacts. Source with with oscillations and a filter with natural frequencies, a filter. They interact. The natural frequency, a frequency at which a system tends to oscillate in the absence of any driving or damping force. Okay. It don't mean a thing if it ain't got that swing. Natural frequencies. They're from Duke Ellington. The 1 degree of freedom. We have a rigid mass and an ideal spring. And mechanical scene. So there's an equation here, m times x double dot, m times acceleration plus k, the spring stiffness, times x minus u is 0. And k is the spring stiffness is 1 divided by static compliance. And f, the natural frequency is 1 divided by 2p times k divided by m. It should be according to the laws we have. According to the fundamentals in chapter 1.4, we have the same equation as this. It's just omega 0. It's called W0 is this square root, and frequency is a W0 divided by 2 pi. Natural frequencies. Okay. 2 degrees of freedom now. A little bit more complicated. And then we have the natural frequency, open tube, source, it's white noise, not a clear pitch percept, need to source to sharpen the tonality. Here a fixed string, the source impulsion, clear pitch percept. When a resonance, when the frequency of the source matches one of the mode of the filter, the amplitude of the oscillation will be amplified. You can see here opera singer, and here the glass is broken. Yes, there's a resonance here. Acoustic impedance. This is defined by acoustic impedance Z is the same as acoustic pressure divided by acoustic volume flow. In fundamentals, the acoustic volume flow is defined as volume velocity, so it should be the same. The ease of playing and the stability of the note depend on the height and narrowness of the maxima or minima of the function of the Z impedance as a function of frequency. A mode can defined as a frequency of one of the peaks. Okay, here we have the frequency, and here we have peaks. Mode 1 here, and a conic cylinder is a saxophone. Mode 1, 2, 3, 4, 5, yeah, and the frequencies here. We see the multiplus, 500 Hertz nearby, and the next frequencies are multiply of 500. And here for flute, there's a cutoff frequency as a little bit more than 2000 Hertz, maybe also for other instruments. Yes. Yes. The sound, this is just repeating the source filter model. The filter can affect the source as in a trumpet. The frequency of the lip is tuned to the natural frequency of the resonator. Okay, the filter can affect the source as in the trumpet. The frequency of the lip is tuned to the natural frequency of the resonator. See here, upper lips, lower lips, air in mouth at pressure above atmospheric air, and there is a mode here. And vocal cavity, see a nasal cavity, oral cavity, larynx, lungs pressure. I mean, larynx means strubehoved. And we see time domain here, and magnitude of the magnitude as a function of the frequencies. And we have a vocal tract here, filtered signal frequencies, and the frequencies domain here, magnitude of the frequencies. So now we go to the idiophones. Definition: any of a class of musical instruments such as a bell or gong, whose sound is generated by striking, rubbing, plucking, or blowing the material of the instrument itself, not under any special tension. Idio from Greek means own or distinct. Phone means sound. So idiophones is any class of musical instruments such as a bell or gong whose sound is generated by striking, rubbing, plucking or blowing the material of the instrument itself, not under any special tension. Acoustics of a percussion bar with 3 ends. And we have some stuff here. A regular bar mode, first 1 mode, second mode 2 modes, third mode 1, 2, 3, 4 modes, and so on. The frequency F1, F2 is 2.06 times F1, and then 5.40 times F1, and the fourth one 893 times F1. You see the numbers here, they are not whole integers. So it's a little bit, it's not like a flute, for instance. It's not harmonics. Position of the notes. Okay. Yes, comes here. In this formula, the ends of the ends frequency is this little bit complicated term, pi times the speed of sound in the bar times the thickness of the bar divided by 8 in the denominator times square root of 12 times L in squared. L is the bar length. And all this thing multiplied by mn squared. Mn is 3.01112 and then 5, 7 and 9 and so on. So the first four modes of vibration of a rectangular bar. The solid and dashed lines indicate the positions of the bar at opposite phase position in the cycle. Yeah. Acoustic of a percussion bar with free ends. There are no harmonic overtones. Fn is, as you see the term here, Fn is proportional to L 1 divided by L squared. Fn is proportional to L minus 2 or proportional to 1 divided by L squared. And Fn is also proportional to the thickness. Yes, and the term comes here again. And VL is speed of sound in the bar. Striking in the middle will reduce the second mode. If you strike here in the middle, will reduce the second mode. A resonator is needed to amplify the fundamental frequency. A resonator is needed to amplify the F0, the natural frequency. So we have some questions here. Given we have some materials, pine wood, brass, copper, oak wood, iron, glass, aluminium, steel, speed of sound in those materials. And given a thickness of 1 centimeter, T is 1 centimeter, calculate the length of a pine wood bar that will produce a first mode at 27.050 Hertz. And then 3 centimeter and will produce a mode of it's oak wood at this 4186 Hertz and so on. We can calculate it on by hand or using InspireCast or whatever, MATLAB. So I can just do the first of those two. The first one is 1 centimeter length of a pine wood bar with this speed of sound and a first mode of 22.7.5. We have to calculate. Yeah, here is InspireCast solve. The first one is pine wood with a speed of sound of 3,300 meter per second and the thickness is 1 centimeter. We put in the formula and Mn is 3.0112 and it should be squared according to the formula is equal to 27.5 and you get a length of a positive 1,11 and the same with oak wood. We have it's the same with oak wood with 3,850 meter per second and the thickness of 3 centimeter and you get about 7 centimeters. Thank you. So one